Welcome to part 2 of this video series. On this video, we'll be taking a look at maximum entropy, and we'll be creating an expression in order to calculate the maximum entropy of a probability distribution. So let's take a look at how we can do that. First of all, let's assume that we have n number of items, say there's like 1,000 of them, and we want to arrange it in different groups. Say we have group 0, group 1, ... all the way up to group B. And out of all of these 1,000 items, we select certain items and we put it in group 0. We put certain amount of items in N1, and then we distribute it across all of the groups, and finally we end up with NB items in group B. So, all the ways that we can arrange all of these items, assuming that every single item in N are unique, is actually the permutation of these items. So the permutation can be calculated by this formula. So it's the factorial n factorial divided by n0 factorial times n1 factorial times ... times nb factorial. This can also be expressed as n factorial divided by the product sum of ni factorial, where I goes from 0 to B. Now, in order to find the maximum entropy, all we really need to do is maximize this expression. So this expression has to be maximized. But the problem is that we're dealing with factorials here, and especially we're dealing with factorials of really big numbers. So 1,000 factorial is not an easy number to calculate. It takes a lot of computational resources. So in order to get over that, we need to find some mathematical ways that we can make these calculations easier. So what we do here is that we have, say we have an expression natural log of x factorial. If we expand this out, what this basically turns into is natural log of x natural log of x0 plus natural log of x1 plus natural log of x2 plus ... plus natural log of xn. And this can be written as a summation. So this would be the summation of natural log of xi, where I goes from 0 to n. Now, we can do a integration approximation of this summation. So basically what happens is it goes from 0 to n, where ln of x dummy variable with respect to dx dummy variable. Now after this we can also do a trapezoid approximation, which basically tells us that this would be equal to x times natural log of x minus x plus 1. This is where the Stirling's approximation comes in. So what he basically says is this value is approximately equal to this, such that we can ignore this 1. So basically our approximation is ln of x factorial is equal to x times ln of x minus x. So this is our Stirling's approximation. Now let's take a look at how we can use this in our permutation formula. So right here. So what we have is basically, if we take a natural log of our permutation, so natural log of perm, what we get is the natural log of n factorial minus the natural log of the product sum of ni factorial. So we can use the Stirling's approximation on this one, and essentially what we get is n times natural log of n minus n. Now this term can be written as the summation of the natural log of ni factorial, where I goes from 0 all the way to b. Now I'm just going to leave these terms right here, and I'm not going to copy them over throughout this thing. So let's expand this form out. So again, we have this form right here, and this can also be written as the summation of n times natural log of n minus n. Again, I need to put i's here. So we have that. If we expand this out again, this is simply going to be summation of ni ln of ni minus plus the summation of ni. Now, let me copy over what we have right here, minus n. So, an interesting thing is the summation of ni is simply equal to n, because we've already established that we're taking everything in n and distributing them over these groups, so their sum always has to be equal to n. So we can cancel this term with n, and what we end up with is n times ln of n minus summation of ni ln of ni. Now again, let's turn this into probability. So what we have is the probability of item I is simply equals to the total number of occurrences of I divided by the sum total of all the occurrences. So this means that we can represent ni as the product of its probability times the total sample space. So let's substitute that over here. I'm just going to not write that again. So that's going to be summation of pi n times ln of pi n. So yeah, there's that. What we can do from here is say the summation of pi n, let's put a bracket there, and we can turn this into ln of pi plus plus the natural log of n. Let's keep going. What we can do from here is we can take this n out because it's just a constant. So let's say n times summation pi times ln of pi and minus n times summation, where'd it go? Looks like I made some mistake here. Let's backtrack a little bit. Let's get rid of all of this. So right here we substituted ni with pi n, the probability of n and the total the sample space. What we can do from here is summation pi n, and this would simply be ln of pi plus ln of n. And then from here what we can do is separate these two out. So this would be summation pi n times ln of pi minus summation pi n times ln of n. So we have that. Yeah, so what we can do from here is let's bring this n term out because it's a constant, so we can write that as n times summation of pi times natural log of pi minus, let's bring these two terms out because they're constants. So what that becomes is n times natural log of n times summation of pi. Now we know that total sum of the probabilities is always equal to 1. So this term turns into 1. I'm going to start writing this term again. So n times ln of n minus n times summation pi natural log of pi minus this term is n times ln of n. Now we see that these two terms cancel out as well. So what we end up with is basically minus n times the summation of pi times natural log of pi, where I goes from 0 to b. So let's ignore this term for now as well, because it's simply a constant. So therefore, our maximum entropy is simply equal to the minimum of summation I equals 0 to b of pi natural log of pi. So we went all the way from having to maximize a term this complicated with really big calculations like factorial of 1,000 to a simple calculation of simple summations and probabilities. And we know that probabilities only range from 0 to 1, so we're not dealing with big numbers anymore. So yeah, that's an easier way to calculate the maximum entropy of a probability distribution.